Welcome learners. Welcome to Black Slides Online, the place where you learn the sciences, namely physics, chemistry, mathematics, biology, agriculture, and some on-demand subjects. We meet now to revise the 2026 Lilongwe City Mock Chemistry Paper 1. We have the opportunity to revise a paper from the capital city, Lilongwe City Mock Chemistry Paper 1. In my assessment, this paper is very good paper. And that's why I brought it here to revise with you learners. If you are watching our video lessons on YouTube, our YouTube channel called Black Slides Online Secondary School, consider subscribing to the channel so that every time we upload a new video lesson, you are notified. So we are revising the 2026 MSCE mock exam from Lilongwe City. Lilongwe City, in case you're wondering what schools or which schools are included in the Lilongwe City mock exams, schools including Likuni Girls and Boys, Chaminade Marianist, Lilongwe Girls Secondary School, Chipasula, not Chipasula, but Chinsapo, including private schools such as King's Foundation, and many others. Those are just some of the schools, but there are many who write this mock in Lilongwe City. So welcome once again. Without much ado, let's get down to the business of the day. Welcome learners. Invite your friends, families and friends. Inform your friends it's possible to revise papers on this channel. All you have to do is subscribe to the channel. So this is Chemistry Paper 1 from Lilongwe City. Don't miss out the opportunity to revise this great paper. I give credit to the teachers and examiners who prepared this paper. The paper is rich in exam-style questions. That's why I thought I should bring it here to revise with you learners. Welcome learners. Welcome to section A, which is 70 marks. We are asked to answer our questions in this section. So we have no questions to skip. We have to answer all the questions in the spaces provided. Question number 1. define a rate of reaction. We shall define a rate of reaction in the following manner. Rate of reaction is simply the change in concentration, mass or volume of a reactant or product per unit time. That's how we are going to define rate of reaction is the change in concentration, mass or volume of a reactant or product per unit time. Remember that in a chemical reaction, reactants are used up or consumed and products are formed. So in the course of a chemical reaction, the concentration, mass or volume of reactants decrease, while the concentration, mass or volume of the product increase. So the rate at which the reactant is being consumed or the product is being formed per unit time is what is called a rate of reaction. 1 mark. List two methods of measuring a rate of reaction. The rate of a chemical reaction can be monitored or measured by simply measuring the volume of gas produced over time. So some chemical reactions produce gases. So if we are able to measure the volume of the gas being formed over some time, we can calculate rate of reaction. So rate of reaction will simply be the volume of the gas formed or produced divided by the time taken. So one way to measure rate of reaction is by measuring the volume of a gas produced over time. We can also monitor the rate of reaction by measuring the change in mass of the reaction mixture over time. Let's say we are reacting magnesium with hydrochloric acid. So we measure the initial mass and the final mass of the reactants of the mixture divided by time. That's going to give us a rate of reaction as well. We can also measure the rate of reaction by noting or measuring the time taken for a precipitate to form or for a color change to occur. This is common for a chemical reaction between sodium thiosulfate and the hydrochloric acid. When you react sodium thiosulfate and the hydrochloric acid, the color changes. The color of the mixture, the reaction mixture changes from colorless to something yellowish. So you can monitor that change in color and the time it takes for the color to start developing. That can also give us a picture about the rate of reaction. We can also measure the rate of reaction by simply measuring the change in concentration of a reactant or product over time. Welcome, learners. So know all the ways of measuring rate of reaction so that you can give any two. But in this particular question, we are simply supposed to list two. So don't list all of them because the question is just 2 marks. So each method listed is 1 mark. So just any 2 of these will give you 2 marks. Welcome, learners. My name is Mr. Paul Chilola, your teacher on this platform. In case you have questions, don't hesitate to reach out on the numbers shared earlier on, or simply leave a comment. We shall be able to come back to you to respond to any concerns you have or to any comments that you make. We shall be able to come and read your comments and respond where need be. Table 1 shows bond energies for some chemical bonds. Remember that bond energies are energies required to either break or form bonds in a chemical reaction. So the energy required to either break or form or to break a double bond, a carbon-carbon double bond, is 611 kilojoules per mole. Energy required to break the carbon-hydrogen bond is 413, while that of carbon-carbon bond is 346. To break a hydrogen-hydrogen single bond, 436 kilojoules will be needed per mole. We are asked to calculate enthalpy change for the following reaction. Remember that enthalpy is a chemical name for heat. So in other words, the heat change associated with this chemical reaction. This is ethene reacting with hydrogen gas. Both of them are gaseous reactants to react to form ethane, which is also gaseous. Take note, this is an alkene reacting with hydrogen. As a matter of fact, this must be addition reaction, where hydrogen is simply adding to ethene to produce ethane. Welcome, learners. So, to calculate the heat change associated with this chemical reaction, we shall use the equation heat change, the enthalpy change, delta H is enthalpy change, is simply found by subtracting the total energy absorbed to break bonds in ethene and hydrogen minus the total energy released, bonds formed. Okay, remember that bond breaking is an endothermic process, meaning that these need energy input for them to have their bonds broken down, and the bond forming is exothermic, meaning energy is released when bonds are forming. So the difference in heat content of the reactants and the heat content of the products is going to give us enthalpy change. So first of all, let's find the total energy absorbed from the bonds being broken. So here we are breaking the carbon-carbon bond and the carbon-hydrogen bonds, as well as the hydrogen-hydrogen bonds. So I need to find these, the total energy absorbed in the reaction, and also we shall need to find the total energy released by the reaction in the course of forming bonds. So subtract the two to give us the energy change, the enthalpy change. Welcome, learners. So to find the total energy absorbed in breaking bonds, we shall consider the bonds involved here. For ethene, there's a carbon-carbon double bond, and there's only one such bond there, this one here. So we have 611. 611 kilojoules is required to break the carbon-carbon double bond in ethene. Shall also need to break the carbon-hydrogen bond. There are 4 carbon-hydrogen bonds in ethene. So we take 4 multiplied by 413, which is 1652 kilojoules per mole. So we are done with the ethene. Then hydrogen, there is a single bond between hydrogen atoms. So the heat required to break the hydrogen-hydrogen bond is 436. Since there's only one bond, so we have 1 multiplied by 436. So adding these together shall give us 611 plus 1652, add 436, which is 22,699 kilojoules per mole. This is the energy, the total energy required to break the bonds in the reactants. We do the same for total energy released during bond formation. Since in ethane there is one carbon-carbon bond here, so the energy associated with the energy released in forming this bond is 346 given here. But we have 6 carbon-hydrogen bonds. 6 carbon-hydrogen bonds. So we get 6 multiplied by the energy released during the formation of this bond, a single bond. That's 6 multiplied by 413. Which gives us 242,478 kilojoules per mole. So the total energy released during bond forming, we just add these two numbers. 346 add 2,478, which is 2,828 kilojoules per mole. Then we go ahead to apply our formula. Enthalpy change is equal to total energy absorbed minus total energy released. So substituting, we shall have 2,699 kilojoules per mole minus 2,824. The difference gives us minus 125 kilojoules per mole. Sometimes they will ask you what kind of reaction this is. The sign on the number here, on the value of enthalpy change, tells you what kind of reaction it is. If it's negative, then it is an exothermic reaction. It means energy is being released. The minus sign shows that the energy is being released to the surroundings by the reaction. So this is exothermic reaction. So all the steps shown, we have 4 marks. As a matter of fact, 5 marks. So one step, each step is worth a mark. Welcome learners. My name is Mr. Paul Chilole once again. In case you have questions relating to this question, don't hesitate to reach out. We'll be glad to hear from you what you think about this solution. So go through this and work out your own way, maneuver your own way of doing the same and arrive at the answer which we got here. Welcome learners. Question number 2a. State 2 ways of expressing the concentration of a solution. The concentration of a solution can be expressed in different ways, but the examiner is asking us to just state 2 of the ways. Right, so one way of expressing concentration is moles per cubic decimeter, written as moles per cubic decimeter like this, or simply molar. So this is called molar concentration or molarity. Molarity, remember, is the number of moles per unit volume of solution. So moles per cubic decimeter, but we can also express concentration as grams of solute per cubic decimeter. This is called molarity with L throughout. Molarity. It's different from molarity, first one. This is called molarity. M-O-L-A-L-I-T-Y. Molarity. This is molarity. There's an R. There's a difference there. This one is concentration in terms of the grams of the solute per cubic decimeter. Another way to express concentration is grams per liter. Grams per liter. So you can convert decimeter cubed to liter. In fact, a decimeter cubed is the same as a liter of a solution. You can also express concentration as parts per million. This is very common in analytical chemistry. Parts per thousands, parts per hundred, which is called percent. You can present concentrations like that. You can express concentration in these different ways. We can also express concentration as percentage by mass. So you take the mass of the solute divided by the mass of the whole solution, or the weight of the whole solution, multiplied by 100. So it will be percent. We can also have concentration expressed as percentage by volume, where I take the volume of the solute divided by the volume of the whole solution, expressed as percent again. So any 2 ways for 2 marks. Don't write all of them, just know them. Know all of them. It's important to know many things, so that when you are asked for 2 of these, you should be able to give those without struggle. In a titration, 25 cubic centimeters of hydrochloric acid of unknown concentration was titrated against 20 cubic centimeters of 2 molar sodium hydroxide, to which phenolphthalein was added. Name the standard solution in this titration. So recall that a standard solution is one whose concentration is known exactly. So here the solution whose concentration is known exactly is sodium hydroxide. Its concentration is 2 molar, expressed as molarity. So the standard solution is sodium hydroxide solution. How do we know that? Give a reason for the answer to be. It's because we are told the concentration is 2 molar. The solution whose concentration is known exactly is called standard solution. So it has a known exact concentration. We can even quote it is 2 molar. So its amount is precisely known and used to calculate the known concentration of HCl. Even if you simply say it has a known exact concentration, full stop, you can still get 1 mark there. Welcome, learners. In case you have questions relating to these questions, don't hesitate to contact us for any queries you might have. To see, work out the molecular formula of a compound if its empirical formula is CH2O and has a molar mass of 180 grams per mole, given the relative atomic masses of carbon as well. As a matter of fact, this must be 12. The relative atomic mass of carbon is not 1, it's 12. And that of hydrogen is 1, while that of oxygen is 16. So empirical formula is the simplest formula of a compound. So we have CH2O as the empirical formula of the compound, whose molecular formula is not known and we are asked to find it. So to proceed, we shall need to calculate the mass of the empirical formula. So the mass of the empirical formula will come from the data that is given here. There's 1 carbon atom there. Each carbon atom has a mass of 12. Make sure you correct this one. This must be 12, not 1. Since there's only 1 carbon, so we have 12. And we have 2 hydrogen atoms. Each hydrogen is 1. So you take 2 multiplied by 1. That's 2. Then you have 1 oxygen atom there. You take 1 multiplied by 16. The total mass of the empirical formula is 30 grams per mole. Then you find the ratio, the number of molecules, rather the number of units, these things that can be made out of the given mass of the compound. So you simply take the given mass, this 180 grams, divided by the mass of the empirical formula. we are finding how many of these we can obtain from the given mass. So you take the mass of the empirical formula, which is 30 grams, divide into the mass of the compound, 180. So dividing the two gives us 680 divided by 36. Please check this calculation. Then you multiply each atom in the empirical formula by 6. So you take 12 multiplied by 6. No, excuse me. Multiply 1, which is 1 carbon here, multiplied by 6. That will give us 6 carbon atoms. Then we have 2 hydrogen atoms multiplied by 6. That will give us 12 hydrogen atoms. 1 oxygen atom multiplied by 6 is 6 oxygen atoms. In other words, multiply the whole of this by 6. So by the end of the day, we shall have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. So that the molecular formula now is going to be C6H12O6. As simple as that. Welcome, learners. This is Black Slides Online. In case you have not subscribed to the channel, consider subscribing. That will accord you the opportunity to be notified every time we upload a new video lesson. Welcome, learners. Number 3, define a conjugate acid. I see that this question has appeared in many mock papers from different schools and divisions. Definition of a conjugate acid. I think elsewhere I also saw define conjugate base. But here we are asked to define a conjugate base. We shall define a conjugate base as simply the species or the substance formed when, remember we are defining a conjugate acid. We shall define a conjugate acid as a species. A species is just a substance formed when a base gains a hydrogen ion, which is also called a proton. Or put simply, it is a base with a hydrogen ion added to it. That's the simplest definition. So a base to which a hydrogen ion is added is called a conjugate acid. One mark. The equation below shows the reaction between an acid and a base. We can tell from the reaction, from the equation, what's going on here. This is propanoic acid, I guess. Yes, it's propanoic acid is reacting with water to form a propanoate ion. This one is called propanoate ion, and a hydronium ion. So what's happening here is the propanoic acid will donate a proton, which is hydrogen, to water to form a propanoate ion. So propanoate ion is just a carboxylic acid minus, in this case, it's propanoate ion is simply propanoic acid which has donated its hydrogen. So the hydronium ion formed is a conjugate acid. Here, water is behaving like a base because it's accepting hydrogen from propanoic acid. So therefore, the hydronium ion, H3O plus, becomes a conjugate acid. So that if we take the reaction backwards, note that this is reversible reaction. So if we take the backward reaction, it means the hydronium ion is the one to donate hydrogen to the acetate ion. So identify a conjugate base. So a conjugate base in this case is the acid that has lost or that has donated a hydrogen. So this is a conjugate base. So in this case, it is the acetate ion. In case you ask to name this, this is acetate ion. In fact, the propanoate, sorry, I keep saying acetate, is supposed to be a propanoate ion. Propanoate ion, because it is formed from propanoic acid. I'm sorry if I kept saying acetate ion, because an acetate ion is formed from acetic acid, which is the acid found in vinegar. Welcome, learners. Give a reason for your answer. Why do we say this is a conjugate base? Because it is formed. The reason is because it is formed when the acid, which is the propanoic acid, donates or loses hydrogen ion. So it is what remains after the acid has given away its proton. So it's therefore a conjugate base. In this case, the hydronium ion is a conjugate acid. Welcome, learners. Explain why aluminium oxide is amphoteric oxide while magnesium oxide is basic oxide. Recall that amphoteric oxide is one that behaves as an acid on one hand, and it also behaves like a base on the other hand. Amphoteric behavior. It's behaving like an acid under certain conditions as a base. That's called amphoteric. So between these two, magnesium oxide and the aluminium oxide can react with both acids and bases to form salt and water. So the fact that it reacts with both acids and bases, it has both acidic and basic properties, hence it is amphoteric. It's amphoteric because it can react with an acid and it can also react with base. The same substance can behave as an acid, can react as an acid with an acid as if it's a base. It can also react with a base as if it's an acid to form salt and water. So since it has these two properties, basic and acidic properties, hence it is amphoteric. On the other hand, magnesium oxide reacts only with acids. It doesn't react with bases to form salt and water. Therefore, it does not react with bases. Hence, it is basic oxide. It's not amphoteric because it can only react with an acid. In other words, it is entirely a base. explain the difference between strength and concentration of bases. These two terms are very, very important concepts when it relates to acids and bases, and they are the most confused terms. Strength of an acid, strength of a base, and concentration of a base are not one and the same. So the examiner is asking us to explain the difference between these two terms. Strength and concentration of bases. When we are talking of strength, we are simply referring to how completely a base dissociates or ionizes in water. Strength is how completely. I think there's an omission here. Supposed to have the word how. So strength is how completely a base dissociates or ionizes in water. So when we are referring to an acid being strong, it means that we are talking about a base. So when we are referring to a base as being strong, it means that such a base ionizes fully in water, and a weak base only partially, ionizes only partially. So that's strength of a base. It is how completely the base dissociates or ionizes in water in solution. So a strong base ionizes fully, a weak base ionizes only partially. While concentration is the amount of a base dissolved in a given volume of solution measured in moles per cubic centimeter, a cubic decimeter. So strength is about dissociation of the base into ions, while concentration is the amount of the base dissolved in a given volume of solution. Give any two examples of catalysts. First, remember that a catalyst is simply a substance that speeds up a chemical reaction without itself being consumed. That's what a catalyst is. So in chemistry, we have made a lot of catalysts by now, and the reactions that they catalyze or speed up. One of them is iron. Iron is used as a catalyst in the Haber process to make ammonia. Remember, the Haber process is the process by which ammonia is manufactured industrially. So in order to speed up the process, iron is used as a catalyst. Manganese dioxide is another one. It speeds up the decomposition of hydrogen peroxide. When you add manganese dioxide to hydrogen peroxide, the hydrogen peroxide decomposes into water and the oxygen. Welcome, learners. Another catalyst is platinum, used in catalytic converters and oxidation reactions. So know the catalyst and the reaction. That, of course, it's not part of the question for you to mention the reaction which each of them catalyzes. I just thought it could be helpful for you just to be reminded of the catalyst and the reactions that they speed up. Another one is nickel. Nickel is a catalyst for hydrogenation of alkenes, addition of hydrogen to alkenes. For example, converting an alkene such as ethene to ethane, you need this catalyst which is called nickel. I'm sure you're familiar with vanadium oxide. Vanadium oxide is used in the contact process for making sulfuric acid. Contact process, you covered this in Form 3 in a topic called sulfur and its compounds. So the manufacture of sulfuric acid uses vanadium oxide as a catalyst to speed it up, the process up. Welcome, learners. Question number 4b. Explain how a catalyst increases the rate of reaction. Remember that catalyst increases the rate of reaction. It's one of the factors that affect the rate of reaction. Catalyst. So the examiner is asking us to explain how. How does a catalyst speed up the rate of reaction? The role of a catalyst is simply to provide an alternative reaction pathway that has a lower activation energy. In other words, a catalyst simply lowers the activation energy of the reaction. Remember, activation energy is the energy required for a chemical reaction to start. So, if the activation energy is very high, the reaction is less likely to occur. So in order to lower the activation energy, the energy that a reaction requires to happen, we shall need a catalyst. So that's the job of a catalyst. Right? So this means that more reactant particles, once the energy is lowered, more reactant particles have enough energy to react when they collide, and so successful collisions happen more often and the reaction rate increases. So that's what you're supposed to have said for 2 marks. Figure 1 shows the crystalline allotropes of carbon. So we have 2 allotropes here. Remember, allotropes are simply different forms of the same substance. So carbon can exist as shown here by allotrope A. It can also exist as another allotrope shown by this structure. So name the allotrope A. The allotrope A, you would recall this must be graphite. So this is graphite. Remember that graphite is made up of hexagonal layers which are joined together by weak covalent bonds. These bonds here represent weak forces holding the layers together. So it occurs in hexagonal layers. I think these are not hexagons. I think there's an oversight when drawing this thing. This shape must be hexagon with 6 sides. But this one has 1, 2, 3, 4, 5, 6, 7. No. This needs to be checked again. Welcome, learners. So A is an allotrope of carbon, which is called graphite. Explain the structural difference between allotropes A and B. I brought the diagram here so that we can refer to it without having to go back to the previous slide. So we are asked to explain the difference, the structure differences between these two for 4 marks. So I'll be referring to the structures from time to time as we look at the differences. So if this was drawn properly, this is supposed to be hexagon, this shape here with 6 faces. So allotrope A, which is graphite, consists of a flat hexagonal layers. These layers are supposed to have 6 faces. The layers of carbon atoms held by weak intermolecular forces. Alright, while B is a diamond, which forms a rigid, continuous, 3-dimensional tetrahedral lattice with strong covalent bonds in all directions. That's one difference for 2 marks. Each carbon, the other one is about bonding. So each carbon atom in A here is bonded to 3 other carbon atoms. For example, if you look at this particular carbon here, it's bonded to this one, it's bonded to this one, it's also bonded to another one down there, 3 bonds. But for carbon to be full, to have a full outer shell electron, it's supposed to bond with 4 atoms. But here it's bonded, each carbon is bonded to only 3. That means there's 1 electron that is free and it's not bonded. Alright, so we are saying each carbon atom in A, which is graphite, is bonded to 3 others and has 1 free mobile electron. This is the reason why graphite conducts electricity, because of that free mobile electron, while each carbon in B, in the diamond, is bonded to 4 others with no free electrons. For example, if you look at this carbon here, it's bonded to 1, 2, 3, 4. This is why diamond doesn't conduct electricity, because of lack of free electrons. Layers in A slide over each other, meaning this layer can slide over this one, over one another, easily due to weakened forces between them. While the structure of B is hard and inflexible, not flexible, as all bonds are strong and fixed. Structure differences between the 2 allotropes, crystalline allotropes of carbon, graphite and diamond. A has layered structure, I mentioned that already, with gaps between the sheets. There are gaps, these gaps between the sheets, between these, while B has a slightly tightly packed network with no spaces between the atoms. So these are the structural differences between graphite and diamond for 4 marks. Welcome, learners. In case you have any observation, don't hesitate to leave us with a comment, and we shall come back to respond to your comments. But if you want to find out more about Black Slides Online Secondary School, don't hesitate to drop us a message. We shall be glad to come back to you with feedback explaining the joining process. List 2 properties of silicon dioxide. Remember, silicon dioxide is the same substance which is also called silica. That's the traditional name. But systematically, it's called silicon dioxide. It's the substance that is responsible for the hardness of sand. It's the substance found in sand. If you try to break sand, it's very hard to do so because of the substance called silicon dioxide. This is why when in your plate of rice, if there's sand in it, and you will accidentally chew it between your teeth, you really feel that you're trying to break something hard. So that hard substance is due to silicon dioxide, which is found in sand. So we are asked to list 2 properties of silicon dioxide. It has a high melting point because it has very strong covalent bonds, so it doesn't melt easily. Imagine trying to melt sand which contains silicon dioxide. It will be very hard to do. You will require high amounts of heat energy. It does not conduct electricity whether you dissolve it or you melt it. Does not conduct electricity. It is very hard as well. It is similar in characteristics to diamond, which is a form of carbon. What are polymers? We define polymers as simply large molecules which are made of many small repeating units called monomers, joined together by covalent bonds. That's the simplest definition of polymers. And the process of forming such large molecules is what is called polymerization. Welcome, learners. State any one use of polythene. Polythene is basically a plastic. It's a polymer made of ethene molecules. It's also called polyethylene. Polythene. Alright, it's a form of plastic. It's used in making plastic bags, which you call jumbos. They're made from polythene. The low density bags are made from polythene. We also use polythene to produce plastic bottles, which are called PET bottles. And the containers, food containers and other things, the buckets, plastic chairs, all those are made from polythene, high density polythene The low density polythene is used for making plastic jumbos, bags, manufacturing of plastic wraps, and packaging materials. We also use polythene for creating electrical insulation and cable coverings. State one characteristic of thermoplastics. Remember, there are two types of plastics. We have thermosoftening plastics and thermosetting plastics. One characteristic of thermoplastics is that it softens. I'm sure these are thermosoftening plastics which are being asked about. So they soften when heated and can be reshaped or remodeled repeatedly. Characteristic of thermosoftening plastics. You can reshape them, you can mold them into different shapes once heated. Welcome, learners. Explain why thermosets or thermosetting plastics can be heated and molded only once. Unlike thermosoftening plastics, thermosetting plastics cannot be molded many times. Once you heat them once, you only have the opportunity to mold them only once, and when you heat them again to mold them into something else, it will be very hard to do so. The reason is simple. It's because they have strong cross-links between their polymer chains. Between the chains, there are cross-links. Those are very, very strong, and they withstand further heating. So when heated and molded the first time, these cross-links form permanently, thereby preventing you to remold them again. Welcome, learners. So further heating does not soften or melt them because the strong bonds do not allow them to be reshaped again. Figures 2 shows structures of organic compounds. These are organic compounds, different ones. Let's just have a quick glance at each one of them. This one contains a functional group called carbonyl within the molecule. When a carbonyl group is within the molecule, not outside, this belongs to an acanone, also known as ketone. So this is an acanone called the propanone. Propanone because it has 3 carbon atoms, 1, 2, 3. It's propanone. It has a carbonyl group. CO is called carbonyl within the molecule. Let's look at B. B has a functional group of OH. Obviously, it must be an alcohol or acanone. And this is propanone by name. C also has a carbonyl group just like A, but it's not between the carbon atoms. So in this case, this must be an acanal, not acano, but acanal. It's also called the aldehyde, an aldehyde. It's called the propanal. And then lastly, D. D contains a carboxyl group. This is an acid group called carboxyl group. Therefore, it must be an alkanoic acid or carboxylic acid. Carboxylic acid. Since it has 3 carbon atoms, this must be propanoic acid. So the name of D is propanoic acid. Propanoic is the acid that has 3 carbon atoms. Welcome, learners. My name is Mr. Apoch Lola, your teacher. Remember, once again, we are revising a paper from the capital city, from Lilongwe City. This is Lilongwe City 2026 mock exam, chemistry paper 1, written by schools such as Lilongwe Girls, Kinsapo, Bwaira, Likun Boys and Girls, Jaminade, Marianist, and the other schools, including well-known private schools such as King Foundation. In case you have not subscribed yet to the channel, consider doing so that you don't miss our revisions. Welcome, learners. Name the functional group in compound A. I should have copied that structure here for us to avoid going back to the previous slide. But all the same, let's go back and look at A. So functional group in A is this CO. This is called the carbonyl group. So the examiner is asking us to say carbonyl because it's an alkanon or ketone. So the carbonyl group is within the carbon chain. When the carbonyl group is outside the carbon chain, then it becomes an alkenyl, which also contains a carbonyl group, the CO bond, the carbon double bonded to oxygen. This is called carbonyl. Describe a test of distinguishing between compound B and compound D. Once again, let's go back to look at D and B. B is an alcohol with OH, and D is a carboxylic acid. So how do you distinguish an alcohol from a carboxylic acid or alkanoic acid? The test that you carry out to distinguish the two involves the use of phenolphthalein indicator in sodium hydroxide. So add a few drops of phenolphthalein indicator to dilute sodium hydroxide solution. It turns pink. Phenolphthalein added to dilute sodium hydroxide solution will turn pink. Alright, and then add each compound separately, either B or D, separately to this pink solution, and then observe. The observation will be that compound B, which is an alcohol, when added to the pink solution, the pink color remains unchanged, meaning no reaction occurs. So no color change for an alcohol added to the phenolphthalein indicator in a dilute sodium hydroxide solution. So the pink color does not disappear, it still remains there. But with compound D, which is propanoic acid, the pink color disappears. It becomes colorless. The reason is because the acid neutralizes the sodium hydroxide, and that will remove the color from pink. neutralization will take place. So the solution will change from pink to colorless to show that the compound D is an acid. It's propanoic acid. Welcome, learners. So the compound that removes the pink color is D-carboxylic acid, while the one with no color change is B, that's C, an alcohol. 2 marks. It will be up to the examiner to decide how to score these points. Some of them are trivial statements, but I don't see which one is trivial. I feel that there was an underallocation of marks here. It should have been 4 marks, so that we have all these points to be scored, or 5 marks. Welcome, learners. 7D, rather B, state the difference between positional isomerism and chain isomerism. Include relevant examples. 4 marks. Isomerism. Remember that isomers are different structures of the same compound, or compounds having the same molecular formula but different structure formula. Isomers. So we have 2 types of isomers. Of course, we have different kinds of isomers, but here we are limited to talking about positional isomers and chain isomers with examples. So the difference between them is that positional isomers, in positional isomerism occurs when compounds have the same carbon chain, the same functional group, but the functional group is attached at different positions. That's positional isomerism. So the same carbon chain and the same functional group, but the position of the functional group is at different positions. Example, butane 1O. The functional group is the OH, is at the end on carbon 1 here. But butane 2O also has an OH, but it's positioned on carbon number 2. So these basically have the same molecular formula but different structures due to differences in the position of the OH. So the OH is on carbon 1 in one structure here, and the carbon 2 on carbon 2 in the other structure here. Positional isomers versus chain isomers. Here we are just looking at positional isomers in terms of the position of the OH. We could have picked another example like alkenes, which contain double bonds. So in one case, could have the double bond at maybe carbon 1. In another case, maybe the double bond could be on carbon 2, depending on the length of the chain. While chain isomerism, remember we are differentiating the two. While chain isomerism occurs when compounds have the same molecular formula but different arrangements of the carbon skeleton, whether straight or branched chains, with the functional group in the same type of position. So here the The functional group doesn't really change that much. Unfortunately, the example that I've given you does not have a functional group since these are alkanes. So, for example, this is a butane with 4 carbon atoms. It's a straight chain. We can create a branch somewhere, let's say on carbon number 2. Yeah, let's say carbon number 2, where we have a branch, a methyl branch. This is 2-methylpropane, which is branched. This is a straight chain. This is branched chain. They have the same formula, C4H10, but different carbon chain structures. That's the difference between positional isomerism and chain isomerism. In case I've left you behind, you have not gotten the explanation, don't hesitate to leave a comment in the comment section. We'll be glad to come back with rectification. Figure 3 is a diagram showing the reaction between magnesium and silver chloride. So we have magnesium rod. In most cases, magnesium is in form of a ribbon, but that's okay. So we have this magnesium being dipped into a solution of silver chloride. And it's observed that at the bottom of it, the silver is being deposited down here. Explain the reaction. So magnesium, once dipped into silver chloride solution, is going to displace, this is a displacement reaction, it's going to displace the silver ions. From these chloride ions. So the silver metal, therefore, the silver will be deposited down here. And in the solution, we shall have magnesium chloride instead of silver chloride. So explain the reaction. So the explanation the examiners are looking for is for you to say that magnesium is more reactive than silver. This is from common knowledge from reactivity series. If you take magnesium, compare it with silver, magnesium is on top, is higher in the series than silver. So magnesium is more reactive than silver. So it is going to displace the silver ions in solution. So magnesium displaces silver from the silver chloride solution. All right. In other words, magnesium will take the place of silver in this solution because magnesium is more reactive than silver. All right. So the magnesium atoms in the process, the magnesium atoms will lose electrons once dipped there to form magnesium ions Mg2 plus and go into the solution and combine with the chloride ions forming magnesium chloride salt. So silver ions will gain the electrons which have been lost by magnesium, and that will form solid silver metal. That's the one which is being deposited down here, which deposits at the bottom of the container. So magnesium chloride is formed as the new soluble product. So the solution by the end of the day will predominantly be magnesium chloride. Welcome, learners. Write the chemical equation for the reaction. So the reaction happening here is going to involve magnesium solid. This one, the magnesium solid, reacts with silver chloride. So magnesium is going to displace silver here. The place of silver will now be taken up by magnesium. In the process, the magnesium will be displaced to form a solid. That's the one which is deposited here at the bottom. In case you have missed that bit, don't hesitate to leave us a comment in the comment section below. Welcome, learners. Give two uses of electrolysis. Remember, electrolysis is the splitting of a compound using electrical energy. Splitting a compound, in most cases molten or ionic substance, into its elements is called electrolysis. Using electricity. So electrolysis is used in the extraction of reactive metals like aluminium from their ores. Remember, an ore is a compound that contains a particular metal. It's a rock containing a metal. So aluminium can be extracted from its ores using electrolysis. It is also used in electroplating metals, coating metals to improve their appearance or to prevent rusting. Electroplating is when one metal, such as iron, is coated with another metal, such as silver, to make it look good or to prevent it from rusting. The reaction below shows formation of salt by precipitation. Identify a precipitate. Sodium chloride, which is salt, reacts with another salt called silver nitrate to form silver chloride and the sodium nitrate. Identify a precipitate. Remember that a precipitate is an insoluble product. One of these is insoluble in water. It's hard to say unless you already have a foreknowledge of these compounds. It's hard to say, but from our knowledge of what we call solubility rules, we know that it is silver chloride which is going to remain a solid in the solution, insoluble product. A precipitate is the solid product, an insoluble product in a chemical reaction. So how do we know? See, it could be silver chloride. Okay, because we know that all chlorides are soluble in water except chlorides of silver. So this is from our knowledge. Silver chloride is not soluble, so it's going to remain in the solution in the reaction as a solid precipitate product. So the answer there is silver chloride. Write the net ionic equation for the reaction. So all you have to do is write everything, every species in terms of ions. We have sodium ions, chloride ions, silver ions, nitrate ions on the reactant side. This one we can just leave it as it is because it's insoluble, so the ions are not free to move around. But sodium nitrate can be written as Na plus and the nitrate ions NO3 minus. We can do that, from which we identify what are called spectator ions, the ions that are found on both sides of the reaction, and cancel them out accordingly. So what remains is going to be the reaction that forms the insoluble salt. So in this case, for us to form this insoluble substance, it means it's simply silver ions reacting with chloride ions to form an insoluble solid. The others are going to cancel out their spectator ions. So this is the net ionic equation for this reaction. Welcome learners, my name is Mr. Pochilola, your teacher. Okay, I brought this up for you to easily remember which one is going to dissolve in solution. This is just some rhyming poem, I don't know what you can call this. So all sodium, potassium, ammonium salts dissolve away. All nitrates dissolve every day. So we are saying compounds or salts of sodium, potassium, ammonium dissolve in water, as well as all nitrate salts. Potassium nitrate, this nitrate, like here we have silver nitrate, it's going to dissolve in water. Chlorides dissolve, but silver compounds do not. So this is not soluble according to this rule. So silver and lead chlorides will not dissolve in water. Sulfates, all sulfates, think of all sulfates. Potassium sulfate, aluminium sulfate, magnesium sulfate will dissolve in water, but those of barium sulfate, lead sulfate, and calcium sulfate, it's not very soluble, slightly, so it's considered insoluble anyway in solution. Carbonates stay solid. All the carbonates, unless they are sodium carbonate, potassium carbonate, and ammonium carbonate. So these will dissolve, but most of the carbonates are insoluble in water. Welcome, learners. In case you have questions, don't hesitate to reach out or leave a comment in the comment section below. So from the reaction, we can go back. We are asked to identify spectator ions, those which we have cancelled out. The sodium we have cancelled out. Sodium is appearing here. It is also appearing here. They're going to cancel out. The nitrate is also going to cancel out. These are spectator ions, the nitrate ions. So that's what we are asked to say here. So sodium ion and the nitrate ions, these are going to be spectator ions just watching the game. Balance the redox equation below. Redox equation. Redox reaction is one in which one species gets oxidized, the other one gets reduced at the same time. So we can quickly grab that. Let's see what's happening. If you look at zinc, which is an atom, becomes a zinc ion. That means zinc is being oxidized. Iron, which is an ion, Fe3 plus, becomes an atom. That means iron is being reduced. So in other words, the reducing agent here is the zinc. The oxidizing agent here is the iron. Those terms need to come out clear as you are approaching your exams. Welcome, learners. So we are asked to balance this equation. So you don't just put numbers anyhow. You need to look at certain things here. The electrons, the number of electrons lost, and number of electrons gained. So let's start with oxidation half reaction. from here. So you can see clearly that zinc is being oxidized from zinc metal atom to zinc ion. To do that, it has to lose 2 electrons. So zinc atoms lose 2 electrons to form zinc ions. So the oxidation half reaction, therefore, is going to be this one. You just multiply it by 3. Multiply it by 3. The 3 is coming from the charge on the iron here. It's 3 plus. So multiplying to balance that number of positive charges. You will be wondering where we got this 3 from. It's the charge on the iron. Because by the end of the day, our equation must not have electrons in it. So we need to balance them up. So multiplying by 3, where from? Is this one here. So this is oxidation. Remember that during oxidation, the electrons are lost. One species loses electrons. Those lost electrons must be gained by another substance. Reduction, half reaction, involves the change of iron ions to iron metal atoms. So in order to do that, we shall add 3 electrons here. We are adding 3 electrons because the net charge there that needs to be balanced is positive 3. So this must gain 3 electrons to balance out that. So we multiply by 2, which is the 2, this one here. I'm showing you the easiest way to balance these redox reactions. So easy. So multiply this by 2, these 2 here. We produce this equation. So we have these 2 equations. This is oxidation, loss of electrons. This is oxidation, gain of electrons. Notice because of the multiplying we did, the number of electrons is the same now in both equations, only that the electrons are appearing on different sides of the reaction. So we add these 2 reactions together. You see that eventually we are going to have 3 zinc atoms added to 2 iron ions plus 6 electrons will be equal to 3 zinc ions plus 6 electrons plus 2 iron atoms. Take note that the species on one side, like the left-hand side are adding up to each other. Similarly, those which are to the right, they are also adding up together. So by the end of the day, take note that we have 6 electrons on the right and 6 electrons on the left. So these are going to cancel out, like they're going to subtract each other. The result is 0. So by the end of the day, we are going to have an equation which looks like this. Very neat, right? This one here, without the electrons. Welcome learners. Question number 10. Define the term water pollution. We shall define pollution, water pollution, as the introduction or addition of harmful or unwanted substances into water bodies. Water bodies refers to rivers, lakes, seas, oceans. That change its quality. The quality of the water changes due to the addition of such harmful substances, making it unsafe for human use, harmful to aquatic life, and is also unsuitable for other purposes. So such water cannot be used for cooking, even for bathing, or other uses. So it's the introduction of harmful or unwanted substances into water bodies like rivers, lakes, seas, oceans. Name 2 ions that cause water hardiness. The 2 ions that cause water hardiness are calcium ions, Ca2 plus, and the magnesium ions. When these ions are present in water, we say that the water is hard. It will make it difficult to use for washing clothes. It consumes a lot of soap when you use such water. All right. So these are the ions responsible for water hardness. Question number 11. A. What is the difference between limiting and excess reagents in relation to stoichiometry? In chemistry, especially in the study of chemical reactions, a limiting reagent is the reactant that gets completely used up and is going to determine the maximum amount of product formed. So the reactant that is in less quantity is called limiting reagent. It's the reactant that gets completely used up and it determines the maximum amount of product. While the excess reagent is the reactant that is present in more than the required amount and remains unreacted even after the reaction has ended. Calculate the percentage yield of iron in a reaction where 67.3 grams of iron 3 oxide reacts with excess carbon monoxide to produce 41.8 grams of iron according to the equation. So iron oxide reacts with carbon monoxide to produce iron and carbon dioxide. So we are asked to use the given information to calculate the percentage yield. Alright, so to calculate percentage yield, first of all, we must calculate the molar mass of the iron oxide used. So to calculate the molar mass, just add the given values. Here we have Fe2. So we take 2 of these iron, the mass is 56 multiplied by 2. And then we have 3 oxygen atoms. Each oxygen is 16 multiplied by 3. The total mass is 160 grams per mole. You also calculate the number of moles contained in here. The number of moles is going to be equal to the given mass, which is 67.3 divided by the molar mass. Dividing 67.3 by 160 give you 0.420662. This is the calculator value. Then round it off to 0.42. This is the number of moles of iron oxide in the reaction. So the mole ratio, the ratio of the iron oxide to the iron produced is 1 to 2. How do we know that? This is 1 mole, there's 1 here. 1 to 2, this 2. So the mole ratio of iron oxide to iron is 1 to 2. That means the number of moles of iron is going to be equal to the number of moles of the iron oxide, this one, times 2, is 2 here, which is 0.84125 moles. I hope we are together. Then calculate the theoretical mass. So the theoretical mass of the iron produced is going to be equal to the number of moles multiplied by molar mass. So number of moles is this one here, which we just worked out, multiplied by 56 grams per mole. That's molar mass of iron. If you multiply this out, you get 47.11 grams. theoretical mass. All right, so the actual yield of the iron is 41.8 grams. So using the actual yield, this one, and the theoretical mass, this one here, we can calculate the percentage yield. So percentage yield is simply the actual yield is found by dividing the actual yield by the theoretical yield multiplied by 100%. So that's the formula. Okay, so we substitute the values. The actual yield is 41.8 given here, divided by 47.11, which is the theoretical yield, this one. So the final result, the percentage yield which is needed, is going to be 88.78. This is a good reaction. The yield is very high, just high enough. There's just little loss of 11 point something, I think. Yeah. So by stating that, that's 1 mark. Each step is 1 mark. There are 8 marks here to contend for. Lastly, explain what you can do to show that heating hydrated copper sulfate pentahydrate, this is a repetition, hydrated copper sulfate is already hydrate, but that's okay. Copper sulfate pentahydrate means there's water there already. There's no need to say hydrated again. Is a reversible reaction. All right, how can we use this to show that heating copper sulfate pentahydrate is a reversible reaction? So what you need to do first of all is take blue hydrated copper sulfate, pentahydrate, in a test tube and heat it gently. So you heat the copper sulfate gently. The blue substance, the blue solid turns white when you heat copper sulfate. Copper sulfate by nature, the pentahydrate copper sulfate is blue, so it's going to change its blue color to white. And you also see colorless water droplets condensing on the test tube. So hydrated copper sulfate, when heated, will produce white copper sulfate, which is called anhydrous copper sulfate, and water. So let the white solid cool fully, then add a few drops of water. It's like you're driving back the water into the copper sulfate, which was white, which was heated. All right, you're adding a few drops of water to it. The white solid is going to turn blue again, and the test tube feels even warm. All right, so when you add water to the anhydrous means without water. So when you add water to the anhydrous copper sulfate, you form hydrated copper sulfate again, which shows that the process is reversible. So since the change is reversed by heating then adding water, the reaction is reversible reaction given by this. The copper sulfate pentahydrate, when heated, will form anhydrous copper sulfate, which is white, and the water. But when you add the water back, it's also going to form this product, the original product. 5 marks, 5 steps, 5 marks. Take note. Explain how greenhouse gases cause global warming. Remember, greenhouse gases are the gases that are responsible for greenhouse effect, leading to global warming. So explain how. 5 marks. So sunlight reaches the earth as shortwave radiation, which passes easily through the atmosphere to warm the earth's surface. So heat from the light from the sun reaches the earth's surface. So the warmed earth emits heat back into space as long-wave infrared radiation. Infrared is basically heat. All right. So the greenhouse gases such as carbon dioxide, methane, and water vapor in the atmosphere absorb and trap this outgoing long-wave radiation. Effectively, instead of escaping into space, the trapped heat energy is re-radiated in all directions, including